Okay, so welcome again to the Cloud HPC Symposium, and we're at session 4 tonight for applications of cloud-native technology to HPC in the cloud. And my name is Christoph Hagleitner. I'm working at IBM Research and have the honor to chair the session tonight. And our first speaker is Kyle Chard, who is a research assistant professor in the Department of Computer Science at the University of Chicago. And he also holds a joint appointment at Argonne National Lab. He's co-lead of the Global Lab Research Group, where he focuses on developing scalable systems to support data and compute-intensive research. And he's going to talk to us tonight about serverless computing, high-performance function as a service. So without further ado, please.
Awesome. Thank you, Christoph, and thank you to the organizers for the invitation to speak here. I think this is a particularly important symposium to bring together, and our group has spent a lot of time over the last decade sort of bouncing back and forth between the world of cloud and the world of HPC. And I think there's some real opportunities in terms of what we can do to leverage each other's work to potentially build better services or better systems for users. And I should say that a lot of my work really is motivated by scientific users fairly broadly. So you'll see a lot of that in the talk as we go through it. And I should also say that, of course, building these systems is more than just me. There's a lot of people involved in the projects I'm going to speak about, and I acknowledge them there, some of them at the bottom of that first slide. So I think we're at an interesting sort of inflection point with HPC, and things are changing in three, probably at least three important ways. The first is that resources, I guess, are becoming much more specialized, much more heterogeneous. We're seeing different types of architectures, different types of accelerators, et cetera. And almost by definition, if you're specializing resources, you're distributing resources, right? Everyone can't have everything. So we're going to have this sort of ecosystem of computing systems, HPC through to the edge, that are going to have different capabilities. They're going to be right for different types of jobs. And of course, that leads to the second point, which is workloads are increasingly changing. We're seeing, certainly at Argonne, that a lot of workloads are becoming interactive in real time. A lot of HPC workloads coming off to analyze data coming off instruments, et cetera, to send back results relatively quickly. We're seeing a lot of machine learning training and inference tasks. And as a result, the workloads are really moving away. Well, maybe not moving away, but becoming more diverse than they have in the past. And then the other big thing we're seeing is that users are changing, that we're getting a much more broad user base that need or want to adopt HPC in their applications. And part of that is, again, because of the workloads changing, that if you're doing machine learning, you need to be using relatively large scale resources in order to train a lot of these algorithms. And we're also seeing with these new users coming to these HPC systems that we're seeing different interfaces, that people are adopting things like Jupyter notebooks, more interactive style programming environments. So if we think about sort of HPC and cloud, and I'm coming at this more from the HPC world, what can HPC learn from the cloud providers? I think what we've seen over the last, 10, 15, 20 years now is that cloud really has succeeded in this vision that isn't particularly new since the 50s or 60s around commoditizing computing, turning it into a utility where people don't have to worry about the nuts and bolts and they can basically provision computing infrastructure on demand. And to achieve that sort of vision, there's been a lot of innovation from the cloud computing world, particularly around things like interfaces to computing, around adoption of virtualization, and really taking a lot of these ideas that were used in sort of other ways and really bringing them to the mainstream audience. I think of things like authentication, authorization, these web standard security models. We think about the adoption of economics and markets to actually provision resources. And so I think in a lot of ways, cloud has really pushed the needle a long way forward in terms of that commoditization of computing. And we've seen, of course, that HPC has adopted some of these ideas. We see now virtualizations fairly prevalent in HPC centers. We see containers being used of different varieties. We see object storage being associated with HPC systems. We see backfill queues, et cetera, et cetera. And so an interesting question I sort of pondered when I was preparing this talk was, what can we actually learn from what cloud has done? And what can we take potentially across to the HPC world? And there's a few things that I really think have been key focuses of the cloud community that have really led to this widespread adoption. The first is this focus on usability and removing barriers. I think cloud really has focused on the user community. They've tried to move closer to the user as much as possible rather than stay sort of stagnant, right? They bring services and platforms to their user communities. They're really focused on reliability and availability. They decided they can't tell their users that every Monday they're going to be offline for the day. That's not an acceptable sort of way of provisioning a service, and if you want to have widespread adoption. They're focused on scalability, but from the perspective of elasticity, where you can sort of very easily scale things in and out as you need to. They're focused on very flexible allocation models. And one of the big things I think is this unopinionated sort of nature about what the right usage is. I think they've sort of been embracing of many different types of workloads, even if it wasn't what they originally envisioned their platform being used for. It's been this very welcoming sort of, let's just bring these compute workloads on board and we'll find out a way to satisfy them over time. And recently, I think we're seeing a lot of these ideas come together in the new sort of serverless offerings from cloud providers. This is almost like the next logical step. They've abstracted everything from the hardware through to the data management, and now let's abstract even the virtual infrastructure. So this whole serverless world that the cloud platforms are pushing really abstracts everything below the sort of very highest level programming element that users are using. And one of the most common, or probably the sort of flagship serverless product, is the function as a service platform, or function as a service paradigm, where people can basically work in terms of programming functions. They define a very simple programming function in the language of their choice. They pick that language, they register that function, and then they can invoke it. They can invoke it one time, they can invoke it a billion times, they can share it with their friends. And that's completely elastically scalable, right? So we can invoke this function with very little latency. We can do it whenever we want. We can run it many, many times concurrently. And it's very simple to update, very simple to deploy in the first place. And so if we think about the previous slide about sort of what we can learn from cloud, I think FAS really is sort of a really great example of taking this very user-focused abstraction type model and making it accessible to a very wide range of users. What we see from FAS at the moment, though, is it's offered by a cloud provider. And of course, that makes complete sense. Why would a cloud provider care to, well, with an asterisk on the edge, but why would a cloud provider care to enable FAS execution beyond their cloud platform? And so what we see is these almost silos where people, they get locked into their cloud provider of choice, they start defining their functions, they start executing them in that FAS environment. So you have a single provider, which provides great service. You have a single location, a single API where you submit your tasks. You execute your functions in a homogeneous environment. It's very, very, very easy. It's integrated with the cloud data management fabrics, et cetera, et cetera. What we've been starting to wonder in our group is, well, FAS seems like a really great interface to computing. It really addresses a lot of those challenges about how do I actually make use of infrastructure? How do I scale my workloads without really needing to worry about the underlying details? So a question for us has become, well, if we think about having this FAS interface to the world, what would we need to do to actually enable that? And the benefits, of course, here are that we can provide sort of access to much more heterogeneous computing elements. We can provide access to remote computing elements. So if we think about what we still want this single nice FAS interface where I can register a function in the cloud and run it. I can monitor it through that interface, but we'd like to be able to leverage sort of very diverse resources behind the scenes, while still providing homogeneous execution environment. We don't want to have to be changing our function for different places it executes. We still would like it to be transparent, that we don't need to worry too much about what's actually happening behind the scenes to provision our infrastructure and run our function. We'd like to link with some data management capabilities, probably a little bit different than the object storage or cloud data fabrics that exist within a single provider. But this has been a sort of area of interest for our group over the last 3 or 4 years. And we've built a system which we call Funkex, and we've sort of positioned it as what we call a federated FAS system. So moving away from this single provider model and moving to this federated ecosystem of computing elements behind the scenes. And so the basic idea is that we have a cloud service in the sky that looks like any other FAS system. You wouldn't know if you're talking to Lambda or our system. But behind the scenes, the actual execution of those functions is occurring on compute endpoints that are registered by particular users. We still have the same notion of being able to register functions and share them with your friends. We still have the same notion of providing sort of elastic, transparent execution of functions, transparent with an asterisk on it, because you do obviously need to determine where you want that thing to execute. So this is sort of a quick schematic of what the Funkex platform looks like. So as I say, it's a federated function serving ecosystem. You see down the bottom here that we have what we call endpoints deployed on various systems, in this case deployed on some sort of cluster and deployed on a laptop, and we have this cloud service in the sky. So these endpoints really are responsible for managing infrastructure, provisioning the resources to run the functions, and enabling that homogeneous execution environment within a container, where containers, of course, are different in HPC systems than they are in, say, Kubernetes or laptops, etc. And then this Funkex service in the sky, as I said, provides the same type of infrastructure as a general cloud-hosted FAS system. And the thing that I think is particularly cool about this type of model is that we add this extra variable or this extra dimension to the FAS world, where we can basically choose where we want to execute functions. We can choose where we want to execute functions based on capabilities of resources. Perhaps we need a specialized device to execute a particular function. We can also execute where a function may be closest to data so that we avoid costs of moving data, or potentially where a function may execute cheapest. Maybe it's cheap to use a particular system on which we have a large allocation. We can leverage fast machines, we can leverage accelerators, et cetera, et cetera. So in order to actually provide these capabilities, we have a couple of sort of big components of the system. There's the cloud service that's implemented as a REST API in running on Amazon Web Services. And we have this agent software, which is deployed by users to manage the execution of functions on their compute resource. So this agent essentially is just a Python-based piece of software. It's pip installable. You can, on the right there, you just pip install your Funkex endpoint, you configure it, and you start it. When you configure your endpoint, you tell it how to speak to the resources on which it's deployed. So you might be deploying it on a laptop that's using Docker. You might want to say, well, I'll allow it to use 3 cores on my laptop, and that's it. Or I might be deploying it on a supercomputer. Here, a picture of the forthcoming Aurora supercomputer, and I need to tell it, here's the scheduler for how I provision nodes. Once I've provisioned nodes, here's how I deploy containers on those nodes, or here's the Conda environment I need to have set up in that node to be able to use it. For a lot of that, we use the parcel workflow system or parcel workflow library to actually manage infrastructure. That Funkex agent is responsible for managing, essentially it takes a queue of tasks from one or more users, and it's responsible for farming it out to the resources it has available, scaling elastically based on whatever users allow it to do. We support managing execution in various types of containers, although in many cases, a lot of people actually use this agent just running in a Conda environment because it's a single user agent. Most often you're running your own workloads, and therefore it's a relatively safe sort of thing to be able to just running in a Conda virtualization environment, using virtualization very loosely there. We do allow endpoints to be shared with collaborators, although we are a little careful about that because on some facilities, of course, that's not really permitted. So in terms of sort of what this looks like to a user, if we've set up an endpoint, how do we actually then go and run some things? And this is, Dennis, where I probably could have demoed, but I didn't think about it until you mentioned it. But what you want to do is we have a Python SDK. You basically go through like a standard SDK for using a web service. You define a client, you register a function. Here, just a standard piece of Python code. You call this Funkex register function, passing in that pointer to the actual function. Funkex does the serialization, puts it as a blob in the sky, and can actually push that blob down to an endpoint to invoke it with some arguments when you come to that point in time. So at the top here, I'm showing a little individual, potentially in their Jupyter environment, registering a bunch of Python functions that are supposed to do some compute and return some results. Once I've registered a function, I set access permissions on it. I can then allow myself or others to execute it. Unlike traditional FAS systems, in which invocation basically is just a function ID plus a set of input arguments, in the Funkex system, you of course have to also supply an endpoint ID in which you'd actually want to execute that function. So this is showing a very quick example there of using our tutorial endpoint, basically just passing in that ID, the ID of the function we just registered, and 3 arguments that we'd like to send to it. The Funkex system is then responsible for dispatching that to the endpoint. The endpoint's then responsible for running it and sending the result all the way back again. The result is cached at various layers, and there's a bunch of sort of queue semantics there to make sure those results are reliably transmitted back again, but they're actually held in our cloud service until a user comes back to retrieve them for up to a couple of days at the moment, I think. So that provides that sort of fire and forget model. You send off 1,000 functions to execute, you come back a day later and collect your results. Alternatively, we have an asynchronous API where you can actually have futures that are filled in by results when the results are actually ready for you. We've done a bunch of testing of the Funkex system in terms of scalability. It's always hard, I guess, to compare performance to sort of black box cloud providers, but we focused here on deploying an agent on a couple of supercomputers, on Theta and Cori, Theta at Argonne, Cori at NERSC, and sending through some of the worst case sort of function types, worst case being no ops, which is running nothing. So it's basically all overhead, 1 second sleep tasks through to 1 minute stress tasks. And you see here the strong and weak scaling shows moderately okay performance up to a couple of thousand concurrent containers running with these very short tasks. Of course, the longer the task, the less overhead, the better the performance would be. But the biggest thing, I guess, here is that we showed that we can scale up to 130,000 concurrent containers, while with the asterisk there again on there is some overhead to execute those things. So that's sort of the end of the system we've built. In the last part, in the last 5 minutes of this talk, I wanted to cover some of our experiences using the system for various scientific applications. So of course, being the flavor of the month, and maybe we shouldn't keep mentioning COVID, but one of the things we've worked on over the last year or so is building data pipelines for exploring therapeutics that may inhibit the COVID virus. And so, of course, when you look at these types of workflows, as I know everyone here today is quite familiar with workflows, they're composed of individual tasks that need to run. Many of these tasks actually run for short periods of time, but when you're thinking about screening millions or billions of molecules, that adds up fairly quickly. So we have this pipeline that we developed. The boxes in blue are things that we actually ran with Funkex. So things like canonicalizing smiles, molecular smiles, computing features of those smiles, fingerprinting the smiles for comparison, etc., and even generating images of those smiles that subsequently people fed into neural networks to try and process this and determine. The ultimate goal of the pipeline here is to determine therapeutics or drug candidates that look similar to things that we think might work well. One of the advantages of using the Funkex system for this was we were given a lot of computing resources at the time. A lot of people volunteered their computing resources actually around the world. And so one of the big questions was, well, how are we going to make use of these things together? And by deploying Funkex on these different systems, we were able to very easily route the functions down to separate it up to go across many of these different computers concurrently, and to choose the systems that happened to be online when we were actually running some of the big campaigns that we were doing. A second example, and one that I think is really an increasingly common use case, is around automation and around these sort of automated high-level pipelines, for example, for analyzing data coming off instruments. And so we have another system as part of the Globus project called Globus Automate, which is really about representing and managing these automated pipelines at a very high level. You can think of an automated pipeline at a much higher level than, say, a traditional science workflow. A science workflow running on an HPC system, these automation pipelines running across an ecosystem of data and compute resources. So you see here, we have some instrument. I think this is serial crystallography. It's acquiring data at some rate. We then pass it through this big blue arrow of functions, of which you'll see a bunch of Funkex logos in there, where we're running quality control. We're checking that it addresses a need. We're then analyzing some data to generate a crystal map. We're producing some visualization that a researcher can actually view. And then we're sending the data back again that the researcher can adapt their experiment on the fly. So those are sort of two examples of science use cases. The other thing that we've found Funkex has been particularly useful for, and this is probably no surprise given the sort of platform model of clouds, is for building other applications on top. So we have sort of a handful now of applications that have been built on top of Funkex, building on top of the APIs that Funkex provides. One of the ones we have had most successful is with this DL Hub system, which is really, it's a system for publishing machine learning models. There's a schema there to define the model. And then we use Funkex as a generic runtime to actually be able to execute those models that are published. So a researcher can come along and say, well, I want to use this great materials informatics model that was shared to me by my friend. They can actually come in, they can find it, and then they can invoke that model on their own data to produce inferences. And so we have a provisioned system at Argonne, we're actually now at the University of Chicago resources, in which we actually run those inferences when we need to. We have another example similarly for manufacturing and machine learning. So this is a platform called MDML. It looks relatively similar to a combination of the last two use cases. And given the time, I think I'll skip over this one. And we'll go to the last slide. So probably people out there are thinking, well, so this FAST model seems useful. What have our experiences been in terms of applying this to science and applying it in the sort of research cyber infrastructure environments that we work in? So we have here a list of things that we have found over the last couple of years of using this thing to be advantageous, and a few things that we've found to be potentially a little bit more difficult. So I think the biggest thing is the usability. I think we've heard from a lot of our users that the Funkex system makes a lot of this stuff a lot easier for them. It allows them to work entirely in Python. They don't need to worry so much about the federated distributed nature of where they want to execute things. The web-based authentication model, they're working entirely in terms of OAuth. Being able to address new use cases around event-based and real-time processing, et cetera. And the sharing, I think, has been particularly useful in that it's a very simple sharing model. In terms of some of the negatives, so clearly FAST is not suitable for everything. You do need to decompose applications into function level things that can be run, while you could have a function that just execs a command like a binary on a system. In practice, that's probably not the major use cases. Some systems, of course, some applications don't really lend themselves to being broken up. Data sizes can be problematic. Containerization in HPC, I think we all know well, doesn't always work, and you need to change between container models given the different system you're running on. And so with that, I will conclude. We have a Funkex website there, funkex.org, and there's a binder, an online My Binder notebook where you can run through a tutorial and get some experience using this thing, pointing at our tutorial endpoint. Thank you.
Thank you, Kyle, for an excellent presentation. Do we have any questions for Kyle?
I have a question. I want to make sure I understand there's a function endpoint ID, but there's a function ID and an endpoint ID, and the endpoint ID is the resource that you want that function to be run on. Yeah. And so if it's a function that requires a GPU, then the user knows to identify an endpoint ID that has a GPU. Is there any notion of trying to automate that process and figure out automatically? And if not, is there any notion of remembering where a certain function ID was targeted before, what type of endpoint ID, and using that, over time to automate that process more?
Yeah, so that's a great question. So one of the problems we have as academics is we get excited about these types of questions. So we're trying to run the Funkex project very much as a production system. So we're trying to keep our thoughts on exciting things we could do a little bit separate. And so the mandate for the Funkex team to build this thing, we've tried to set a very clear bar. We're not going to focus on any of that. We just want to very explicitly manual allocation of functions to resources. But of course, in our research team, we had a master's student that just completed their master's, and we have a PhD student that is continuing with their work in this space to sort of look at more automated scheduling in these types of environments. And you can think there's a bunch of variables, from one example being how do you match a function to the type of resource it executes on. The master's student, he actually looked at various things like how well does a function perform on a particular resource, because every CPU is different, they run at different speeds. How long does it take to transfer data to that resource? How long am I going to wait for cold start time on different systems, from spinning up a container to grabbing a node in a queue to provisioning a node in the cloud? And he tried to wrap all of those features into this sort of meta scheduling architecture that would automate decisions across this continuum of computing devices. And it worked relatively well, but it was a master's thesis. So it's nowhere near production, but I think there's some super fun things we can do in that space, and hopefully our PhD student is going to explore a lot of that. And that's the fun of this sort of federated environment, right? That we can actually ask those questions and start exploring. But potentially we need a middle ground, because sort of what you suggested was you almost need some resource matching capabilities, quite coarse-grained matching. You don't need to go to the nth degree and magic automated scheduling. Yeah, which I think is a great suggestion.
Yeah, I'm thinking there's a lot of interesting thesis topics in this area, I bet. Thank you. An excellent talk too, by the way.
Thank you.
Kyle, this is Dennis. Again, a great talk, but then again, I've used Funkex, as you may remember.
I was going to say, I'm scared of your question. You actually use this thing. And you're going to probably tell me I lied.
I had great fun using it. It was a lot of fun. I just mentioned the one thing about, I had one case that I didn't think was going to work that did work, where I had a small device which was running a local web service that I couldn't access outside the little device, but using Funkex, I could invoke a function which invoked the web service, which got the results that I wanted and brought it back. And that was fun. And just the whole thing I thought was this is an advertisement for Funkex. Anybody, if you want to look at this, it's easy and it's fun. And I spent about a couple of weeks just playing with it.
And you wrote a great blog post for us as well, which we appreciate on our website. Yeah, we should have you come around all our talks, Dennis. That's a great way to wrap things up.
So
Kyle, do we have another minute for a question?
go ahead.
Okay.
One last.
So the underlying frameworks and federation with other frameworks and serverless functionality is sort of the gist of my question. Does it integrate well with kubeless and other types of frameworks?
No, we haven't focused on integrating the agent software with other serverless systems, and there's a bunch of serverless systems that work well on their own infrastructure. So that's another great potential path forward, because no one's going to want to replace their OpenWhisk or their kubeless or whatever that's set up on a nice Kubernetes cluster, but potentially adding it to this federation would be interesting.
And I think it's gonna gel well with what I'm going to talk about as well.
Oh, cool!
There's a lot of opportunity there.
Awesome. I look forward to it.
Great.
Excellent. So thank you again for a great talk. I'll save my question for later because we actually got to move on to our next speaker, who is Bruce Damora, who is a senior technical staff member in the hybrid cloud department at IBM TJ Watson Research Center in Yorktown, where he leads efforts to develop HPC and AI workflows on the Red Hat OpenShift platform. His other interests include computational steering and visualization for high-performance computing applications, and he has led the performance analysis effort for the Coral system, as well as the application system bring-up for BlueGenQ that preceded those systems. For people who know Bruce before, in his time before he joined IBM Research, they might have run across him when he was leading the OpenGL graphics API efforts and served as the representative on the OpenGL architecture review board. Today, Bruce is going to talk about minding the gap, navigating the transition from traditional HPC to cloud native development. And let me start sharing the screen here, because that's going to come from my own screen. And off we go.
Good morning, good afternoon, good evening. My name is Bruce Damora from IBM Research in Yorktown Heights, New York. And the title of my talk, Mind the Gap, Navigating the Transition to Kubernetes, is focused on transitioning HPC apps to Kubernetes clusters. So there's a lot of challenges to make this transition to Kubernetes. Clients that I've spoken with have certainly experimented a lot with containerization, but less so with Kubernetes. And so just as they ran into security issues with containers, they have some of the same questions about Kubernetes. And we've even seen some things in the news lately where people have hacked into Kubernetes clusters. So this is just kind of an area that needs to be investigated a little bit more. Scalability, that's been talked about for a while. And maybe some of these Kubernetes deployments can scale up to 5,000 nodes, but more often than not, it's 1,000 nodes or 1,500 nodes, and certainly HPC clusters, even if they have GPUs, can be larger than 5,000 nodes. And then scaling multitask applications is very different than scaling the number of users. And I think Kubernetes has been optimized more for scaling the number of users rather than the number of tasks per application. So I think a lot more work has to be done in this area. High performance networking, although you can install high performance networking on a Kubernetes cluster and even access it from applications running on pod, the actual Kubernetes platform components don't take advantage of high performance networking. And what I mean is they don't take advantage of RDMA and the low latency communications that is provided by that. And I think that's particularly important when it comes to scalability. If you don't have all your components that can communicate with each other with the low latency communications that's provided by things like RDMA, then it's harder for the cluster to scale. Other challenges, parallel file systems. IBM and Red Hat support the container storage interface for Spectrum Scale as an operator that can get installed on an OpenShift cluster. That's not really been tested, at large scale because, and frankly, there's not a lot of, 5,000 node, Kubernetes clusters around. People will say, oh yeah, we've deployed a large cluster, but it's often on VMs in the cloud. So it's a little bit different. Accelerator support is still pretty limited. Certainly NVIDIA GPUs are supported and there's NVIDIA GPU operators that can be installed. But what about other types of accelerators or even other types of GPUs? I know AMD has got a prototype, but it's not widely distributed yet. And I don't know I haven't heard anything about FPGAs, graph cores, and other AI accelerators. I know that there is some work being done in that area, but nothing is been distributed yet. Scheduler support, HPC users are used to mapping tasks to threads, to cores, to sockets, however they need to map the application tasks to get the best performance. And that could even change depending on the app or the data set. The Kubernetes scheduler was really designed for long-running microservices and single task at that. And so it's not really adequate for HPC users. So our proposal is not to deploy a full Kubernetes cluster for HPC users, rather to use a Kubernetes cluster as a control plane. And we would use the Kubernetes cluster to actually provision bare metal compute nodes. The compute nodes would not run any Kubernetes components, no kubelet, no kube proxy. The compute nodes would have high performance networking installed, whether it be Rocky or InfiniBand or whatever. And applications would be scheduled on those compute nodes with an HPC class scheduler. So as I said, the Kubernetes control plane would be used for provisioning. It would do this by leveraging a component called Metal Cube that was developed within the Kubernetes community. It's open source, but it was derived from OpenStack Ironic, which was designed to provision bare metal compute nodes. So once you install Metal Cubed on a Kubernetes cluster, you can use it to provision other nodes that are not going to be part of the Kubernetes cluster with the OS of your choice, whether it be a standard stock OS or one that you customize. It will work with either Redfish or IPMI Pixie Boot. We've been experimenting with Redfish because of the additional security, interoperability, and just having a more active development community. And we're pretty happy with the results. The caveat here, though, is not all server vendors support Redfish, or if they do, they didn't adhere to the spec, exactly as it was written in. So there's slightly different behaviors between different vendors, but that's going to be changing, I think. Our Kubernetes control plane would host what we call login pods, and a login pod would be in the same roles like a login node, except it would be a pod running on a Kubernetes worker, and it would contain the user or the workload development environment. So if the user was inside a login pod, and presumably they would SSH into that pod, they do that on our prototype, they would be able to build their app and have access to all the libraries and utilities and frameworks, et cetera, that they needed to build their app. And then they would launch their app from there. It would look like they were on a login node for all practical purposes. And we can switch these login nodes in and out as much as we wanted, and we can have a variety of them and a number of them depending on the number of users that we had. And the beauty of these is if one should fail, it will just automatically get rescheduled on another Kubernetes worker, because that's the resiliency that's built into Kubernetes. Our Kubernetes control plane would also host scheduler and telemetry and file system master processes. All these components have master and client processes. The master processes could easily just run on Kubernetes workers, where the client processes, which would be basically systemd processes, would run on the bare metal compute nodes, just like they do today. And then would also use the Kubernetes platform for long-running utilities and services like Jupyter Lab, visualization services, database services, et cetera. I think it'd be very good for those types of services. And whereas the applications tend to be multitask, these other services could be single task, and you can run multiple instances of them and hence scale the service with the number of users. These types of services are very common across the data center anyway, so it would make sense to install them. It would get provisioned by our service node, our initial service node that would provide DNS, DHCP services, ingress to the rest of the data center or the public cloud or whatever. And we would deploy this smaller Kubernetes cluster, smaller than the bare metal number of bare metal nodes that we're going to deploy, but it would consist of masters and workers. The workers would host various services like Metal Cube, which we would use for provisioning the bare metal compute nodes, Jupyter, login pods, and then these master processes that I spoke of earlier. Once we had our control plane deployed and stabilized, we would start provisioning our compute nodes, and we would use Metal Cube to do this. It would be very similar to provisioning bare metal compute nodes today. Instead of, we use XCAD at IBM, but other vendors have different cluster management software, but they all kind of operate on the same principle. You need to be able to interface with the BMC on the compute nodes. You need to have some type of configuration file that has the BMC MAC address and the management network MAC address and BMC user login and password, et cetera. You set up those same types of configuration files. It would be with a YAML, because that's what the Kubernetes control plane would recognize. So you create these YAML files that would be used to configure your compute nodes, and then Metal Cube would actually communicate with these compute nodes via Redfish or IPMI and start to provision these nodes. Of course, you need DNS services and DHCP services and HTTP services for that matter. So these compute nodes can get at the OS image. The OS image can be customized and can be stored, where on an HTTP server that the compute nodes would be able to get at. And you would start your provisioning process, and you could install as many of these Metal Cubed pods as you wanted to. Maybe you need more if you have a larger cluster. And so you have multiple instances of Metal Cube running. You would also have your Slurm masters installed, your GPFS master, and your telemetry. In this case, I have Prometheus here, but there's other telemetry services available. And on your compute nodes, you would have the client systemd processes that went along with this. And they would all be running like they normally do today. we would maybe create a Prometheus metrics exporter so we could communicate information about the health of the node, and fan speeds, and heat, and health of the GPUs, et cetera, back to the Prometheus master running on the worker nodes. And then since Prometheus comes with another visualization component, Grafana, it would be very easy for the system administrator to get a visual snapshot of the health of the system. So we think this is a very big value add. You'll notice in this picture that I have an IB network switch that's connecting a couple different storage media, GPFS and object store, both with the worker nodes and the compute nodes. And that's because when we're in a login node, or we've logged into a login pod, I should say, when we go to launch a job, we need to have access to that source code and that binary. And so we need a common file system or object store for both the compute nodes and the worker nodes. And so hence we use our IB network in this picture to connect those together. Our login pods would have a variety of software. This is kind of a superset of everything that I could actually think of. And they would be customized. So if you were primarily doing AI work, you might just have, PyTorch and TensorFlow or whatever. If you were doing more HPC work, you might have a larger variety of libraries, et cetera, more than are actually shown here. I didn't include things like Cocos and Trilanos and those very common HPC libraries. And as I said before, these are not single type of login pod. There could be multiple login pods with slightly different software environments installed. And when I say installed in the pod, it's basically a containerized version of the development environment, because the pod is just a place to launch containers. The scheduler is another issue. And in this picture, I'm using Slurm. The login pod would have a configuration file that was already built, and that would have all the information, specifically the pod names that would allow it to connect to the Slurm master control process. And the Slurm master control process would be launched via the system administrator using an operator or Ansible or whatever. The compute nodes would have the Slurm daemon running as a systemd process, and they would also have their etc. host file configured with the IP addresses of the Kubernetes worker nodes. That's specifically the worker nodes where the Slurm control master process is running. And so you can have this communication back and forth. Now, on the Kubernetes worker node where the Slurm control master is running, there would be a node port service that would map the worker node's IP addresses and port to the Slurm controls pod IP address and port. And that's how we would manage that communication and connectivity between the login node, the Slurm control master process, and the Slurm daemon systemd process running on the bare metal compute node. The MPI jobs have some similar issues. We chose to solve them slightly differently. The main issues there is that if you launch an MPI job from a login pod, the compute nodes don't really know about the network that the pods are running on. They don't know about the pod network. So you have to add that route. So if you want the ORT daemon to be able to connect back to the login pod, which it has to do. The other problem there is that if you are launching multiple MPI jobs, same user, same login pod, there needs to be some type of port mapping. And so we create a load balancer that maps jobs to different ports. We're going to do all this via an operator that gets installed and configures all this appropriately. So in the end, we have a control plane that is made up of some number of master nodes, some number of general worker nodes that are going to host things like all these master processes like Jupyter notebooks, like visualization services, database services, etc., metal cubed, etc. And then some number of login worker nodes that are going to host login pods. And that's where the user is actually going to log in to these pods and do their work. And then the compute nodes, that can be one big homogeneous cluster, or it could be a heterogeneous cluster, as I have depicted here, where you have base compute nodes, large storage nodes, accelerator compute nodes, etc. And all these are going to be connected by a high-speed network of the client's choice. So that's the path that we've been going down now, but there are some future considerations here. And one of them is Kubernetes is not standing still. It's evolving very quickly. It has a very active development community. And so schedulers are one of the areas where I think that needs to be addressed first. And IBM, Lawrence Livermore, and Red Hat are collaborating to create a kube Flux scheduler. For those of you that do not know, Flux is a high-performance scheduler designed by Lawrence Livermore. It was really intended to be a follow-on to Slurm, but it hasn't evolved quite that quickly. But in the meantime, they're looking at creating a kube Flux scheduler. Claudia Masali from IBM is leading that with her counterparts at Red Hat and Livermore. And this would just be a scheduler that any user could specify in their YAML file if they were to launch a Kubernetes job. And so I have the link here to the GitHub where they're storing some of their source code for that work. Jitter mitigation, big problem on large clusters because of OS noise and all the system D processes, et cetera. It gets worse if you're adding Kubernetes because you have all these kubelets and kubeproxy and all these other Kubernetes services that are running on the node. Nelson Gonzalez, who did a lot of work on the original Coral cluster, has actually done jitter mitigation work on a Kubernetes cluster and gotten very good results. The caveat here is it was a smaller cluster. It was less than 30 nodes. And we just didn't have a large cluster available. But he did run high performance workloads, the same types of workloads that were run actually on the Coral clusters. And so, we did get a good idea of the effectiveness of his jitter mitigation techniques. And it was very, very, very good results. I mean, basically eliminated almost all the overhead noise from, Kubernetes components, certainly, and got performance on par with just a plain bare metal cluster. Networking, RDMA for Kubernetes control plane components is something that IBM team is investigating in Yorktown, and Mellanox provides RDMA support for pods. So an application that gets launched from a pod can actually use RDMA. There's an SRIOV operator that Mellanox distributes, and I've seen it in the Red Hat OpenShift hub, and so you can use that. And then MPI, IBM's done some work, and there's a GitHub link for that work. And there's also the kubeflow work. And then once again, scalability is an ongoing challenge. Bear Crop Science has deployed a 15,000 node Kubernetes cluster on a Google Kubernetes engine and has gotten good results with one particular workload, but I think other work needs to happen to really test that out across a variety of different workloads. In the meantime, while all that's happening, we're going to pursue this transitional path that I proposed here, where we just have a Kubernetes control plane and bare metal compute nodes. So thank you very much for your time and for listening to my talk, and look forward to your questions.
So, thank you. And we actually do have time for one or two questions.
So, Bruce, I really enjoyed that. I think your work is amazing. The one thing so I got the impression just at the end that you view this entire project as just transitional until somebody figures out how to do Kubernetes at big scale. It doesn't seem that way, but is that what you intended?
It's tricky because everything's moving, right? Kubernetes is moving. The complexity of HPC and AI is moving. So, yeah, I mean, I think I'm a little bit torn because on one hand, certainly to IBM, it's a value if we have, a full Kubernetes cluster, in our case, OpenShift. But I think the reality is it's going to be a while before we get there and before clients are really ready for that. And the one thing I didn't mention in this talk, which, maybe it's obvious, I guess, but I mean, even if you solve all these problems, there's millions and millions of lines of HPC and AI code that has not even been containerized. And so, let alone, have YAML files created and stuff for Kubernetes deployment. So I think this transition is going to be a long, slow transition. Yes, that's what
I think you just gave a very good reason for doing what you're doing. I mean, there's a lot of stuff just having to redo it for Kubernetes into sort of a giant microservice version of what it was before is daunting. In some cases may not be possible.
Absolutely. You're probably right.
Other questions? No, I have. Yeah, go ahead, Ilkay.
I feel like my talk is my question, actually. I would love to discuss at the end of it.
We'll get to that in a second. But Bruce, there's one question. When I look at the architecture diagram, it looks like one of the strengths of running these things in the cloud, apart from all the weaknesses, is that you can dynamically scale the size of a cluster and partition it into more clusters. Is that something that you have in mind with your design as well?
Yeah, I mean, I think the idea is to make not only the Kubernetes cluster dynamically scalable or as dynamically as you could, but also the bare metal cluster. So you can, potentially pull from the bare metal pool and increase the size, the number of Kubernetes workers, or vice versa. And then the other thing that probably wasn't really shown, I think I had an ingress bubble there, but you could potentially use the Kubernetes control plane as a conduit to public cloud also. So if there were situations where you needed to burst into public cloud, or you just needed additional resources for apps that did not have all the high performance and scalability requirements that most of your HPC and AI workloads need, you could potentially then just burst those into public cloud. So yeah, I guess hopefully that answered your question.
Absolutely. So thank you again for an excellent talk.
Thanks.
And we're now moving to the last and by no means least presentation of this session, which will be presented by Dr. Ilkay Altintas, who's a research scientist at the University of California in San Diego, but also is the Chief Data Science Officer at the San Diego Supercomputing Center, as well as founding fellow of the Data Science Institute. She's the founding director of the Workflows for Data Science Works Center of Excellence and the Wi-Fi Lab. The WORKS Center specializes in the development of methods, cyber infrastructure, and workflows for computational data science and its translation to practical applications, while the Wi-Fi Lab is focused on artificial intelligence methods for an all-hazard knowledge cyber infrastructure, becoming a management layer from the data collection to modeling effort, and has achieved significant success in helping to manage wildfires. Beyond her passion for workflows and data science, she's also an instructor in the field of big data science and has reached more than 1 million learners across all the continents of this planet. She's received numerous awards, among them the 2015 IEEE SDSC Award for Excellence in Scalable Computing for Early Career Researchers and the 2017 ACM's HPC Emerging Woman Leader Award in Technical Computing. And before all that, she did a PhD degree at the University of Amsterdam in the Netherlands, also knows Europe. And without further ado, she's going to talk to us about composable systems and early application experience. Please go ahead.
Thank you for the long introduction. So I'm going to talk about what I refer to, or generally gets referred to as composable systems. And I'll talk about the expanse and some early applications in expanse. And I think it relates to the first two talks.
Sorry,
so,
just to interrupt here. Can you move to presentation mode? Exactly, perfect. Yeah.
I moved a while back, but I think it might be a little slow. I can turn off my video if that continues. So yeah, I was saying I would like to talk about expanse and how we combine expanse with some other Kubernetes clusters in a federated fashion together with some of the NIB applications that we use. And this came from, like we just heard from the last two talks, a similar need. Right? A lot of workflows and the ecosystem around that has everything in it these days, like big data, computational science, are very heterogeneous in nature. There's a lot of AI, data science workflows applied to it. And these applications are really a breed of their own in a way. And they require this continuous AI integration. And often they embrace the digital continuum from the edge to cloud, HPC, and even these days, exascale workloads. And there are many different templates here in terms of how these applications get integrated or look like. One of them is this dynamic data-driven workloads that we have an observed data collection and we select some interesting science from it, so to say, to parameterize simulations or ensembles. And at each time step, we learn from the results of these simulations or ensembles and sometimes even compare it to the real-time data to keep the closed loop nature of the application. So there are a couple of advantages here. Some of it is reduction of the simulation workload or the need, because then you can be more targeted towards how that parameterization works. So we don't have to create a huge system or an ensemble. And the other part of it is sometimes by iterating and learning from data and comparing things, we are able to get into account or take into account the things that are not anticipated. And this happens a lot in especially applications that are now changing fast with the effects of climate change or COVID was mentioned. So these type of closed loop learning from real-time data applications that we refer to sometimes as urgent computing is becoming highly dependent on this type of heterogeneous integration. And when you look at this particular template and many others similar to this, is simulation ensemble still tends to be a lot more traditionally high performance or high throughput computing heavy, and traditional HPC storage or distributed computing gets applied. And when you look at the left side here, or the downstream, so to say, or upstream, we are seeing more of the AI workloads, which I refer to as capabilities. These are NIB processing units, NIB chips, post-more type of or big data type of components in the computing ecosystem. So then being able to compose this in heterogeneous dynamic workflows, it really makes a difference for these applications. And this wasn't the capability in the traditional HPC ecosystem. And often it's not workflow anymore. I refer to it as a team flow sometimes, because it's not just one group, it's multiple groups working together to solve, especially when AI versus simulation are two different camps that needs to bring their work together. And there's a lot of socialization and collaboration related capability the systems also have to provide. And I think those systems also should enhance the teamwork using AI themselves. So when we talk about AI integration, it can come in different places and works that way. So some of the new requirements, I think they were similar in the earlier talks: interoperability or heterogeneous integration and interoperability of the systems, scalability dynamically when needed, and often when we talk about big data, on-demand interactive access, at least notebook-like capabilities, and also this continuous performance measurements, which takes the systems from being black boxes to at least gray boxes, so we can actually take decisions based on the load and the dynamic changes in the system availability. And Kubernetes, for instance, was mentioned just before, is a system that can give us some of these as an ecosystem of tools, some of these capabilities. But when we look at the yellow boxes here, what could be the reference architecture? That's where I was trying to get to here. The systems themselves now can be containerized or become a part of a federated architecture. And we could have, in one computer, we can have everything, but we could have federated set of computers through composition that we could get the best of both worlds. But there are some challenges that I'd like to discuss about that, of course. And the resource management on top of these resources, container orchestration, optimization, these are new resource challenges that are actually very difficult, still very difficult to achieve. And then services, these are anything that runs on these systems. It could be models, traditional simulation, but it could be notebooks running, training, inference type of modeling components. And on top of all of these composable services, often run either serverless or as microservices, as we discussed. There's this workflow integration capability that's required, and it's a different type of optimization and coordination than what we have been doing in the past, with more of static workflow integration and management capabilities. So I think the entire stack is changing, and what changes also on this entire stack is the dependency on the data itself. So we can't just treat storage as a file system access anymore. It needs to be continuous understanding of data, from active data repositories to long-term archives. What happens to the data? How data gets places? You know, data lifecycle management should be in the backdrop of all these different layers. And let's assume we got everything about the yellow boxes right. How do we then move into the blue boxes, which makes these useful for science and team science? Because again, one person doesn't have every expertise anymore, and it's not one executable running on a computer. We are talking about integration of services and the expertise related to those services here. And more of the reproducibility and responsibility oriented challenges, accuracy, privacy, explainability, ethics. These are at the heart of a lot of the components, and the systems actually can enable us to achieve some of these in the long term. And if you look at on top of this stack, once we get all of this right, I think, who are we doing this for? It's for societal applications, it's for scientific applications, educational applications. So translation of all of these into some form of practice that can scale across systems and make it used more and more provide democratic access to the rest of it for different audiences is important. And I think, how do we achieve that type of composability? The biggest requirement for it, in my opinion, at least, is the measurement. dynamically measuring systems and understanding resource needs and availability based on those measurements in white box or gray box fashion is something that is not yet available in current cyber infrastructure systems, especially in the scientific computing systems. Things are changing, but I think we need more emphasis on how much these measurements are needed, and systems that can actually respond to those measurements and help us pivot are needed as well. And then the other part of the thing is, in essence, the measurement and profiling from a service point of view. What are those parameters? How do services actually react to data, react to availability of the computing? What kind of profiles they have? And based on those profiles, how can we map these tools for resource identification and tasks at the workflow level is important. So coordination and resource optimization with the knowledge of the systems in a dynamic data-driven base requires us to have some different tools that actually, AI for AI, so to say, at the system level. We need to be able to first predict, provision, and take smart decisions. So what are the emerging systems? I try to summarize some of the systems that at least I'm aware of. Expanse is SDSC's latest supercomputer, and it has multiple capabilities. It has some heterogeneity in the node composition, but innovative services sort of an advance as Expanse is interactivity, high throughput computing through cloud bursting, and access to other distributed frameworks like Open Science Grid, and also what we refer to as the composable systems. So the idea is to be able to do all of these in one computer so that we could use the right tool for the right application. So to be able to scale the system through bursting on cloud and other high throughput computing environments and federated capabilities through composability is the goal of the system, objective of the system in the first place. So the way composable systems is implemented in Expanse is a part of the cluster is system is reserved as a Kubernetes cluster. And as load changes over time, the idea is to then provision the composable part of the cluster based on the load, and be able to use the CM scale capabilities from Bright Computing to then manage dynamically the nodes between the Slurm and Kubernetes options dynamically. So, and we had to think hard about how we can change how we actually reserve a part of the system and how someone submits requests for composable systems, what's the service model for it. So it's very much of a still capability that requires collaboration with the users. But what I'm going to talk about is those early examples. And Expanse, while we were doing this, was inspired by what we have been doing on the Pacific Research Platform and now the National Research Platform using Kubernetes and high and networking from disk to disk 10 to 100 gigabit connectivity, which is the Pacific Research Platform. The Chase CI project created the Nautilus GPU, or nowadays there are FPGAs and a few other accelerators on it, cluster called Nautilus, to then link a number of gaming GPUs across this PRP network that can provide data parallel capabilities for big data stored on the Ceph storage infrastructure, cloud compatible infrastructure in the backend. And that cloud compatible storage can be integrated with other storage capabilities for further scalability. But the idea is to be able to put as many GPU nodes as possible on top of this storage and networking environment, so that we could take advantage of big data processing capabilities and being able to do things like fast inference on data through, instead of staging things, porting to the storage through network and Kubernetes functionality. And HPRAN, I'm going to pivot a little bit, is a network that actually is set up in the back county of San Diego for wireless sensing and communication, and camera nodes and weather stations and various environmental sensors are on the HPRAN network. Some experiments have happened on HPRAN to then extend ChaseCI to the edge environment, to add some accelerators and things like that to the edge through Kubernetes to generate alerts and things like that on the network. So there's some opportunity there to expand into the edge. And camera sites, meteorological sites, these were where some of these accelerators were inserted. And another project that tried this is the SAGE AI at the edge infrastructure. There, HPRAN plus other NSF networks, Neon, Area of Things, and other environments were extended, and it's currently being extended further with the capability of not just being able to run an inference, but this full-blown software-defined sensing capabilities, and also an environment that we can virtually train models on the data and push them back through a scheduler that prioritizes or manages load through these network components based on scientific needs. So how did they use this for wildfire modeling? And I'll also talk about microscopy applications later on. Wildfire modeling today depends on a lot of data. So it's a very data-driven discipline with environmental sensing, remote sensing, data collection through overhead sensing like drones and flights. A lot of LiDAR type of capabilities of specialized sensing of infrared LiDAR for fuel and perimeter management. And being able to take advantage of this data as fast as a fire is happening during a fire is one of the use cases here. So then we get the weather forecast or real-time weather sensing data, combine it with landscape and fire perimeters or ignition points initially. And we fuse these different data sources and learn from them at times to reparameterize fire simulation tools or programs. And the results then get communicated through maps. So that's how the fire system works. And as I mentioned, during a fire, this is the main question actually. There is a fire right now. Can we fuse what information is available? And sometimes we need to take advantage of AI techniques for that. And where it will go, based on that understanding of what we know about the environment and the fire, what it's doing, about the dynamics of it, where it will go. And it requires this continuous iteration, integration, and integration of computing. Right? At the big data sense, getting the actual wildfire perimeter and comparing it to the fire front that was modeled and learning from them to adjust parameters and selecting those parameters becomes the closed loop. But if we get from that top part of collecting fire imagery and understanding fire right now, and that can be applied to many other parts, right? Understanding the field, what burns in the environment, what's in the path, how they are managing the fire, or understanding weather coming from different platforms and observables and models, and being able to combine it all together to create a closed loop that requires both AI and computing capabilities at different levels. We mentioned SAGE and HPRN. This is one of the experiments that on the HPRN camera sites, can we see the smoke detected and get that trigger to then on the cloud to do fire modeling, or expands to do fire modeling. Or for environmental, like weather monitoring, can we do some of the inference at the edge? Things like that are the experiments and the applications. And that brings me to that first template I shared. This becomes then collecting the fire imagery and using that and how it compares to the integrated model products from the simulations. Can we then use parameterization and close the loop on a regular basis? That's the application that we tested. So how was this done? Right now, a prototype, so to say, or a demonstration example was done by federating Expanse with the Nautilus Kubernetes cluster, where Expanse's Kubernetes cluster that we refer to as enthalpy, and the Nautilus was federated using Admiral2.io federation tool. But the thing here is the storage backend is still combined. So when you have different namespaces with different storage federation is the next challenge here. And there's some difficulties related to storage federation still because of that namespace integration. And I think that's going to be the next thing that we'll see. And this Kubernetes style environments were not built for that. It's pretty homogeneous in the namespaces and very controlled that way. And scientific computing requires, and collaboration requires a little bit further than that. But how was the application I'm talking about with smoke detection implemented here is the smoke detection workflow was executing as inference in this case, the federated cluster. And when a smoke is detected, it gets scheduled on Chase CI. And some of this, in that sense, can be also done in Expanse. So the next thing is actually we were going for is now being able to do the simulations also on Expanse, similar to what we do on Chase CI. And it's not a hard one, it's just we don't need to use Expanse large capability nodes for this type of fire modeling. But as we work on more GPU capable fire models, that's the next step we are thinking of demonstrating on this. Another thing that's being demonstrated right now is then how do we do the same thing on the accelerators on HPRN that was installed by Sage. Right now, Sage, actually, we are using the virtual Sage on Nautilus, on the JCI infrastructure, and doing the training on Expanse. So then we could use both infrastructures, both the sort of the bluish and the greenish nodes, both for training and inference, and also fire modeling. But in the future, when we move to Sage, which is this yellowish boxes, the inference of that smoke detection will happen on the edge itself. So then it becomes really a message that needs to be passed through a data system that triggers the operations. But at the same time, the images that are being collected can be sent to the object storage that is now shared between Expanse and Nautilus, so the training can happen. Again, this points to the storage federation challenges. Things need to be set up for it to work properly that way in terms of the storage and data backend. But as I mentioned, these were 2D models that are okay to run on JCI in a data parallel form right now. But as we move into these 3D models, we both need capabilities, Expanse-like simulation capabilities, and we'll use it more for fire simulations like the ones that we are seeing here. And as we do that 3D modeling, there is more and more needs for different forms of AI and different environments that support this AI. So for dynamic data fusion or accurate modeling, what we refer to as the physics-guided machine learning within the application itself, and then also the decision support optimization algorithms that are running. The next application, do I have 2 more minutes or should I stop here?
If you can wrap up in 2 minutes, that's good.
Okay, is the NeuroCube. This was published in the Big Data Conference last year. NeuroCube is a reconstruction framework using machine learning, or these days referred to as AI, deep learning for neuromicroscopy imaging. And here, the simulation modeling, the whole framework helps us to change the simulation pipeline from, data processing, large-scale simulation, and data analysis to actually combine it with the modeling pipeline of labeling, training, and inference, and then analyzing that. So that helps us to close the loop between the simulation and modeling. The same data processing, large-scale simulation can now be combined so we can actually do a faster form of labeling and reconstruction. And how is Expanse and NRP or the Nautilus being used in this case is the same application for training and simulation lives on Expanse, and then there is the inference part that runs on NRP. And this was built as a framework so others can actually train models and share. So there's a component of it that once the training is done, and this is some sort of data flow works, from different training steps, it could be shared through a model commons, and it goes to a gateway that users can access to those models for using it for inference on their own data and as a part of their own simulation closed loop applications. And when we look at that, there is a lot of similarities in what we all have discussed, I think. The Ceph powers the whole system for storage, and streams of data that needs to be federated across these resources. But what if we have more than one of those, and how do we put those together becomes a challenge. And through that storage backdrop, all of the training and inference, or all the microservices that are running through Kubernetes get sort of like communicate. So I think there's a big gap right now between what can be achieved and what the storage capabilities provide us with. But a lot of people are, I think, thinking about this, and I think making storage a part of the national infrastructure in a way that namespaces can be federated is a huge next step to enable these applications. So all this goes to say this is not a turnkey functionality, and there's a huge gap before it can be. And it requires collaboration between and with infrastructure providers, so between applications and infrastructure providers and within infrastructure capabilities. And end-to-end data pipelines, I think defining those for each application and coming up with different needs and cases to see what we can generalize is very important. And I think that was my question and talk. We had all talked about similar needs and functionalities. How do we actually start integrating these applications and create sort of a combined reference architecture that serves different needs? Thank you.
Thank you very much for a very interesting talk. Any questions? We can still take one or two before we close the session here.
I have one, and I posted it in the chat, but how did you consider other federation software? I think you mentioned Admiralty, but I was wondering if how that relates to things like open cluster management, which I think is a open source project in the Kubernetes community, and just curious about that.
So Admiralty was, I think, one of the first ones. And the reason we picked Admiralty was how easy it made that namespace integration when we first started. And it's also, the storage capability is something I think the developer, I think it's a one-person operation at the moment. I believe maybe it's growing, but the developer was definitely more into providing different capabilities in terms of these different federation opportunities between systems with various backdrops, so to say,
Right.
in terms of storage fabric. So that's why we evaluated and ended up picking it. But when we picked Admiralty, there weren't many, because again, Kubernetes wasn't exactly built for federation. Right? It's
Right.
not a grid tool, so to say.
Right. Thank you. I enjoyed your talk also on just the vision of these workflows spanning, multiple and heterogeneous resources. I think is very aligned with my own interests.
Thank you. I think it is, as you said, there is no one size fits all. And if we can achieve full HPC capabilities under these new frameworks, I think the idea here is how do we put it together with it? And there needs to be a heavy software layer on top at the application level. And how do we make that layer easier for the users in the long term? I think it's a sort of a future-facing challenge.
Yeah.
One other question?
I didn't have a question, but I just wanted to comment that, Ilkay, that was a great talk. It's mind-boggling the scale of the challenges that you have. And so I'm not surprised it's not quite turnkey yet, but it looks very promising. I know your group, and I know how enormous the challenges that you take on are.
Thank you so much. I think working with friendly users right now is good, but we need to think hard about opening this to different groups, especially since Expanse is an NSF computer. So we are providing some seminars and things like that to get the user community to understand this exists, and they can actually come for consulting support and work with us to use some of these capabilities. It's to be proven, I think, still, how that service model works. We are getting a lot of interest in a surprising way, actually. So there's quite a bit of AI integrated workflow needs that's coming our way. Hopefully we can show more applications that are on different application areas. Material science seems to be the next one, for instance, potentially.
Yes, and I think that's a really good way to close it. We're really looking forward to seeing more of that, especially also when it comes to the composability, at which level you're composing really big systems, but we see a lot of research and interest to compose at almost any level of the stack, including from basic hardware up to very high up in the software stack. So again, thank you to all the three speakers for a very interesting session. I hope we will socialize the presentations very widely, and even more so hope that we'll find time to discuss that at some different venues in a more on-prem setting rather than in the cloud. But for today, it is what it is. And with that, I'll stop the recording and close the session.